Good morning. Let's start. I don't think we've done any of these, have we? Yeah. Alright, well these are the sort of series of questions for the right-hand rule. Remember with the right-hand rule, you let your fingers go in the direction of V. V goes into the V, or out of your palm, rather, and then your thumb gives the direction of the force. Or you can think of it like this, where I have my velocity, my magnetic field, and then this is my force. So here in this case, my velocity would be in this direction, the magnetic field is into the page. So what's the direction of the force here? Let me get your clicker thing up. You had a good weekend? Yeah? How's your New York plans coming? Oh yeah, I was telling my wife about that. She thought it sounded exciting.
I don't know, pretty good. We're going into summer. After school.
Oh yeah. You and your family, or just friends?
Yeah, we've kind of been all along like the East Coast, and we've been to Vegas, so we've kind of been there out.
Yeah. We went to Vegas over the summer. We had a good time there. We were just there a couple of days, but it was sort of part of a bigger trip. Hey, Courtney. All right, here we go. So what is the direction of the force? This is a positively charged particle traveling in a magnetic field. What's the direction of the magnetic force? There you go. All right, it's about 5 more seconds or so. I'll stop at 35. Just guess if you don't know. All right, hang on a second, buddy. Yeah, to the left is right. So remember with these, you'll see some multiple choice questions like this, and then, you know, when you're doing the right-hand rule, it's useful to do this as well when you're doing the IJT business. But, and we'll get into mass spectrometers and sort of how generators work, and we'll use this again. But we let our finger go in the direction of V, our middle finger goes into the magnetic field, and then our thumb gets the direction of the force. So it's to the left here. That was pretty simple, but they can get more complicated. Let's try this one. Hey Dash, Alright, I'll stop at 45, 45. Alright, very good. D is the right answer. So, finger's the direction of V, your index finger, magnetic field's in the page, so it's up. So D. That's what I marked, right? D? Alright, how about this one? Stop at 40 seconds, 40 seconds. Alright, B is right. So, fingers in the direction of V, or if you're doing your index finger, and then the magnetic field to the right, so your thumb points into the page. Again, you can either do it like this, where it's like this for this case, or you can let your fingers go in the direction of V and think about the magnetic field coming out of your palm, and those fingers fold towards the magnetic field, and then your thumb goes into the page. It seems kind of tedious, I know, but this is useful because sometimes it's difficult just to think in 3 dimensions like this. So it's useful to be able to think about how these vectors are oriented to one another. Let's see, I forget what the magnetic force was here. Let's just say that the magnetic force on this one, it didn't show up, but let's say that the magnetic force is, does anybody have it open? What is it? It's up? The magnetic force is up? Okay. So our magnetic force here is up. Remember what our cross product is. When we're finding this force, it's the product of two vectors. That are perpendicular to one another. Talking 1 minute, 1 minute. C is right. Very good. So remember, the cross product is the product of two perpendicular vectors. That's what the purpose of the cross product is. It's to multiply two vectors that are perpendicular to one another. And so if I have three vectors that are parallel to one another or anti-parallel, then the cross product is 0. The cross product, the magnitude of it, remember, is QBD sine theta. And so if theta is 0 or 180, then that sine term goes to 0. You look excited to be here this morning. I'm really glad. Because you had such a restful weekend, right? Did you? Restful weekend? Not really at all. Yeah, me either. So, but I'm still glad to be here. All right. This beam of atoms enters a magnetic field region. What path will the atoms follow? It's called a mass spectrometer. We'll get into this and how this works. It's pretty simple. But I have a beam of atoms that enters the magnetic field. What path will the atoms follow? Let it be A is 1, 2 is B. I don't know. Hey, Kristen. Think about what's happening here. Right? I have this beam of atoms. They enter this magnetic field. Think about what is the force that will act on this beam of atoms.
What's number 3 doing?
3 is just a curve. It's curved. Most of you have it wrong right now, so you don't want to rethink your answer. In fact, a couple of you have it right. All right, I'll stop at 120. 120. Again, well, actually, before I go on, most of you still have it wrong. So think about what these atoms are and what happens to them when they enter a magnetic field. What is an atom? What is about an atom? Right. Like, if you're talking about, right, yeah.
Like neutral charge, I guess?
Right. So an atom is neutrally charged. That's the point here. So if that occurs in a magnetic field, what happens? All right, good. Just a few seconds, I'll stop at 204. Okay, good. B is the right answer. They're neutrally charged, right? So the magnetic field doesn't do anything. The other really common answer that you gave was 1, right? But 1, even if it was a positively charged ion, which it's not, but if it were a positively charged ion, you were thinking that it would follow path number 1. So that wouldn't be the case. What kind of force is a magnetic force? We talked about forces that are perpendicular to the velocity, and in this case, a magnetic force is perpendicular to the velocity. You remember from last semester, what type of force did we deal with that was perpendicular to the velocity? We had a particular class of forces that we defined as that. And anytime you have a force that's perpendicular to the velocity vector, no, not normal. That's good. Normal is perpendicular. It is perpendicular to the surface. But here we have a force perpendicular to the velocity. What is it, John? You would do it with your
Yeah,
hands
it's
as
on
sword,
my
right?
head because it's in a circle or
Right.
perpendicular.
What's that? Right, it has to do with circular motion. It's a centripetal force. The centripetal force is, it shouldn't remember the word, right? The centripetal force is a force that's perpendicular to the velocity. That's what it is by definition. And that's what a magnetic force is. It's perpendicular to the velocity. So what's wrong then with path number one if I have the centripetal force acting? Right, it's not a curve, a circular path. So we'll see that with the magnetic spectrometer, mass spectrometer, excuse me. All right, a proton beam enters a magnetic field region and does this. We don't know what the magnetic field is, but what is the direction of this magnetic field? If I have this proton beam that comes in and moves upward like that in that circular path, what is the direction of the magnetic field? So the plus or minus y, plus x, the plus or minus z, correct? Not many of you have the right answer. Only one of you has the right answer. We're not looking for the magnetic, we're not looking for the direction of the magnetic force. We're looking for the direction of the magnetic field. Now, in this case, I know the direction of the force, at least initially, has to be in what direction? At this point, what force causes this motion? Positive what force in what direction? No, not positive. Here, I'm shooting a beam of protons into here, and so they have a velocity that's in this direction. But as they enter this magnetic field, they start instead moving up. So what is the force that causes that for them to move in that circular path? You know? An upward force, right. So I have an upward force that's causing this beam of particles to move up. And now I want to know what direction of the magnetic field that causes that upward force. What type of magnetic field will cause this to occur? Okay, good. It looks like a few of you are changing your minds. That's good. It's a little better. All right, I'm going to stop at 210, 210. Yeah, he's not the right answer. E is the right answer. So here it's into the page. So if I imagine this magnetic field of this region that's into the page, this particle comes in, it has a velocity in this direction. If I have a magnetic field that's into the page, that means the force will be up. So here I have a force that's up, but also notice that that force changes direction. So here my force is up, but here the force is in this direction, it's in this direction, it's in this direction, and it's in this direction. So that force changes, but at all times it's perpendicular to both the velocity vector and the magnetic field. Because if you look, the velocity vector also changes, right? Here it's in this direction, this direction, this direction. It's always, you have this orthogonal system, this right-handed system. It's just that, let's see, it's changing as it goes up through this mass spectrometer. Okay? This region of magnetic field. It's really simple to put a beam of particles into a magnetic field like this, and really easy to measure their path in this way. And so you can use that information to determine a lot of stuff about those particles. Okay, here we have two particles of the same mass, and they enter a magnetic field with the same speed, and they follow these paths. Which particle has the bigger charge? So I have two particles that enter here, and they follow a circular path, and then until they come over here to points A or B. Which of those has the bigger charge? Remember our force, just to remind you, our force is equal to QV cross B. So our force is dependent upon the velocity, the magnetic field, which in this case are the same, but also on the charge. The force is directly related to the charge. Stop at 110? 110? Sorry, I had to think about it. That's not right. That's right. Yeah. So remember, what type of force is the magnetic force? Is this class of forces that cause circular motion? Centripetal. It's a centripetal force. Oh, it is perpendicular too, but it's a centripetal force. And so, if you remember, our centripetal force is equal to mv squared over r. And here, both of these particles have the same mass. So which of these, the one with the small radius or the big radius, has the bigger centripetal force? The what? The small radius. The one with the small r is going to be this one, and it has a big F. Now, if it has a big F, that also means it has a big Q. Follow me? If this one has a bigger force on it, that's forcing it into this tighter circular path, and so that means it also has the bigger charge. So you see, you can discern between two different charges based on the paths that they take through these magnetic fields. We'll get into this some more. All right. What happens in this mass spectrometer? What happens to the kinetic energy of this proton as it travels through this magnetic field? Think back to centripetal forces and what they do to the energy. All right, I'll stop at 1 minute. 1 minute, just guess if you're not sure. All right, and C is the right answer. Remember, if our force is perpendicular to our velocity, then the force does nothing to change the magnitude of the velocity. It only changes the what of the velocity, the direction. Okay, let's do this one. Here, this is like in a CRT, a cathode ray tube, like you have in your old TVs. They would have a beam of electrons that would travel through an electric field, and then they would also have a magnetic field that you can modulate in order to move those electrons wherever on the TV screen if you wanted them to go. So here I have this beam of electrons. They're traveling at a certain velocity, and I have an electric field that's up. That's causing a force on the electrons. And then now I want to know what is the magnetic field that will cause these electrons to go through undeflected. Let me help you out a little bit with this one. The electric field causes a force on these electrons in what direction? Up or down? Down, right, very good. Down is the right answer. Because if you remember, the direction of the electric force is the same as the direction of the electric field on a positive particle. So here we have a negative particle. That's what you're thinking, right? Positive particle? Yeah. So here we have a negative particle, so the electric force is actually down, which is opposite the electric field. So my electric force, I'll call Fe, is right here. That means our magnetic force is in what direction? In order for this to go undeflected. Up or down? It has to be up, right? Because I want this to go so that it has no net force on it. And so we just want it to be opposite the electric force. Okay, so now I want to know, for this beam of electrons traveling through a magnetic field, what is the magnetic field that will give me this magnetic force? Remembering that this is a beam of electrons, which have a negative charge, and so whatever you find with the right-hand rule, you'll take the opposite of that because they're negative charge. And when you do that cross product, like QV cross B, you get the opposite direction. Let me help you narrow down some answers. So here I know that my force is up. That's in the X, Y, or Z direction. It's in the Y direction, right? Our velocities to the right, X, Y, or Z? X. So I know that I have the X-axis and the Y-axis. Those are taken up. Because in an orthogonal system, where I have these three orthogonal vectors, if one of them takes up the X and one of them takes up the Y, then that means the Z is the only one that left. So which of these two answers are the only reasonable answers? Right, only C and D are the only two plausible answers. Because the x-axis and the y-axis, those are already taken up with two of our vectors. And the third vector in this orthogonal system has to be then in either the plus or minus Z direction. And then in order to find that, you need to use your right-hand rule. And don't forget that it's a negative particle. So whatever you find with your right-hand rule, that is with a velocity to the right and a force that's up, whatever you find for that, it's going to be opposite what you think. All right, I'm going to stop at 4:15. All right, there's sort of a lot of thought that goes into this. So here, I have my V to the right, F is up, and so it should be into the page, right? Except what? It's a negative particle. So whatever you find by your right-hand rule is going to be opposite that. So which of these is the right answer? B is the right answer. B is the right answer. Because it's a negative particle. All right, we'll come back to this. We're going to talk about magnetic forces on a wire soon. All right, let's try this quick test. I just want to make sure y'all are okay with your cross product. So y'all just try this on your own. I just simple cross product. I have a particle, negative 10 coulombs charge. Velocity is 2j plus 3k. Magnetic field is 6i plus 8j. What is the force in vector notation? I'll give you a few minutes to try doing the cross product. Remember our cross product, F is equal to Q times V cross B. Alright, and we did these already, but we need to do I cross J. That's equal to K. If you forget, you can always draw your coordinate systems. This is I, J, K, and then do the right-hand rule. We know that J cross I is the opposite of that. J cross K. I'll let you do these on your own. Come back to it in just a second. Use FOIL, just write it out. If you know how to do this method they teach in Calc 3 where you do the little matrix, that's fine too. It's not that much easier. But if you're used to it that way, that's fine. I got it to this point. We just did FOIL, first, outer, inner, last, and multiplied out that those two terms. And then there comes the point you need to find what are these equivalent to. Let's see, J cross I is what? Is negative K. So I know that I cross J is equal to K. If you forget this, you can use your right-hand rule. You can say I, J, and then your thumb comes out of the page. So I cross J is equal to K, and so the reverse of that, J cross I, is going to equal to negative K. So this is negative K. What is J cross J? Is 0, right? And K cross I. Do I know what that is? Is it positive J? Let's see, I always forget. So I, K, no, it looks like it's negative J. Yeah, so I cross K is negative J, or excuse me, did I do that right? No, you were right. You were right, Josh. Sorry, I was doing I cross K. But K cross I is positive J. Okay? K, I is in that direction, J is up. So K cross I is J. If you want to try to memorize these, that's fine, but I don't know. It seems like a waste of space. And then K cross J, what is that? Is it negative I? K, yeah, negative I. So negative I. And now we can combine all these terms and multiply by the negative 10. So I get 120K. Right, I just multiplied this times this, noting that I already had a negative k here, so I got rid of that negative. Plus 0 minus 180j. Was it plus 240i? All right, so that's our our force and vector notation. I want to show you something here as well. You could see this where I ask you the magnitude. It's really simple to find the magnitude of a vector like this. Like this vector, if I were to draw my coordinate systems like this, it's not as simple as we've been doing before, where now I have my z-axis, this is my x-axis, and this is my y-axis. Let's see, looks like this vector is sort of coming out of the page in this direction. It has a positive x component, a negative y component, and a positive z component. So if you imagine your three-dimensional system being broken down into what, 8 quadrants, it's sort of in that quadrant coming out of the board. Y'all follow what I mean, sort of? It's hard to describe it, but my vector has a negative y component, so it's coming down. It's coming sort of out in this direction. All right? If I want to find the magnitude of that vector, I just do the quadratic formula, but you can extend it to 3 dimensions. Have you ever seen this? Quadratic in 3 dimensions? It's really simple. Instead of a squared plus b squared, it has 3 terms instead of 2. So my magnitude of this force would just be the square root of 120 squared plus 180 squared. It's squared so the negative goes away, plus 240 squared. All right, so that's my magnitude. I won't ask you to find the angle of the force. It's a little more complicated to find the angle because in a three-dimensional system, your angle is actually measured. There are what, 3 angles? Because you have to measure from the x, the y, and the z axes. So I suppose some of you engineers might have to do that in the future, probably in other classes, but not in your introductory classes.
So the fourth area you drew is kind of like it's going down.
Yeah, this is my attempt. This is the resultant vector. If I add up all those 3 components, I have a vector that has a positive x component. Oh wait, no. Oh yeah, no, I'm sorry, that was wrong. No, that's right. Yeah, positive x, a negative y, and a positive z. So it's sort of coming out of the board. That's the positive z. It's coming off to the right. That's the positive x, and it's coming down because it's the negative y. All right. So if you're describing the direction of the spectrum, you have to describe the angle of the x-axis, the angle of the y-axis, and the angle of the z-axis. There's probably you'd have to step down and try it, but we're not going to get into that here. I'll look on Wikipedia and I'll show you how to do it. It's pretty easy. All right. Okay. Let's look at the magnetic force on a current carrying conductor. This is just like we did with a particle in free space, except now instead of having our particle move in free space, it's going to move in a wire. So it looks a lot the same. Whereas before we had QV cross B, now we're going to have I times L cross B. In fact, if you look at the units of this IL, right, I, remember, is coulombs per second, and then L has a units of meters. So I'm left with coulombs meters per second. These are the same as the units for QV cross B. These also have the same unit. So identical situation, practically identical, except here, instead of having a free particle traveling with a certain velocity, I'm thinking instead of a current moving in a wire. So you can think of it as a charged particle moving along a wire. But it still works out the exact same way. And so these problems are going to be basically identical. And my force is the cross product of L and V. Generally, when we think of a current in a wire, by the way, we don't think of the current as a vector, because current is a scalar quantity. Instead, we think of the length of the wire. And so that length will have a certain orientation. It'll have a magnitude and a direction. And so just like we had before, the magnitude of the force is ILB sine theta, where I have the vector L, that's the length of the wire, and then I have the magnetic force, or the magnetic field B, and then there's some angle between them. So also, as before, when we take this cross product, we're multiplying the component of one of these vectors, say the y component of B, times L. Right, cross product takes the product of two perpendicular vectors. Right, you can think of this too, as I say, just think of it as a wire, or a charged particle in a wire. So for example here, if I have a charge inside of a wire and it's moving to the right, and there's a magnetic field here, then I can imagine my velocity is to the right, my magnetic field is into the page. So my force on this little charge that's moving in this wire is going to be up. So if you imagine you have a whole bunch of those charges moving through a wire, each of them feels an individual force, and that's going to cause a force on the wire. So this is, oh, and also, don't forget too that we're using the conventional current. And so when we think about this here, we're not thinking about electrons falling in wires. Instead, we're thinking about protons moving, because that is what we assume to be the conventional direction of current. Right-hand rule comes back in this. So it's basically the same here. If I have this wire with the current flowing to the left, and the magnetic field is up, what's the direction of the force on that wire? Well, first of all, I know it has to be along what axis? The X, Y, or Z? The Z axis. So is it in the plus Z or the minus Z? That is, out of the page is the plus Z, into the page is the negative Z. So I is in that direction. The magnetic field is up. Which is it? The negative Z, right, into the page. So into the page is like this. That's the negative Z direction. How about this next one, and then the next one? The current's down. Which axis is the only one that's left? X-axis, right. The Z is taken up to the B. This takes up the Y. Is it plus or minus X? Plus axis to the left, or to the right rather. I is down, B is into the page. So this is the force then is in the positive X direction, or to the right. And this last one, again, the only axis that's left is the X-axis, so it has to be plus or minus X. Ever tell y'all the thing about this? Like, I think this should be, some people have things that they do, and I told my wife that I need a thing. She doesn't think I need a thing, but like, have I ever told y'all this? Dr. Soignier over in psychology, everybody have him. He's like a really cool guy. Like, he's a lot cooler than I am. And whenever you see him, he always gives you a peace, like he does the peace sign. And you know, I think that's pretty cool, and that's kind of him. But he already has that thing, so I can't take his thing. So I was thinking I could do the right-hand rule. Like, hey. So if y'all are looking for a thing, don't use the right-hand rule, because that's going to be my thing. Right. Maybe we run in different circles. So maybe you can use it if you're out. Doing whatever you're doing. All right. So what's the direction of the force on this one? What is it? Positive X. Let's see. So I is in that direction. V is out. Yeah, positive X. All right. And notice too that if I change the direction of my current, if I put my current in that direction, then the force would be in that direction. All right. All right. Let's try this quick test. Think about this. Let's think about it differently. Instead of thinking of it as a force, let's imagine that I'm pushing this current through this wire through a magnetic field, and I want to know what then is the direction of the current. see how y'all do. I'm not sure if that's clear. Is it clear what I'm asking? Yeah. Okay. Well, I'll stop at 110. 110. I'm not sure if we're thinking about this the same way. I'm going to stop at 110 now. Alright, we're sort of split. This is the way I think about this. And maybe you are thinking about it a different way. I'm thinking about it this way. That I have this wire. I'm going to sort of make it big. And I imagine that I have positive charges inside of this wire. Right? So this sort of goes back to the idea that I just have a charge moving in free space. So this charge has a velocity to the right. Right? It's going in that direction. And the magnetic field is in that direction. So my force then on this charge is going to be up. Alright, so I would answer to this A. For those of you that put B, what were you thinking? What were you thinking? Did you have were you not sure? Or what were you thinking along the same line? Oh, you just did it upside down. Okay. You're using your left hand? Oh. Okay, well, I'm just going to leave it at this thing. The point of this is that if you run a wire through a magnetic field, then it generates a current in that wire. All right, which is the idea behind generators. Now let's try this one. It's just simple calculation. Remember, our force is ILB sine theta. I push this with a certain force through a magnetic field. I want to know what is the current that's created in this wire. It's a generator. If I push a wire through a magnetic field, I get a current. Alright, y'all doing really well. I'll just go another 10 or 15 seconds. Try to wrap it up. Alright, I'll stop at 245. A is right. This is simple calculation, right? I just know that F equals ILB sine theta. Right, so F is 12. I want to know I, L is 1, B is 2.4. So I is 12 over 2.4, which is 5. Well, our sine theta, since our sine theta is equal to 9, theta here is 90 degrees, right? So that goes away. That's just equal to 1. That's often going to be the case, right? When they're perpendicular from the other side. All right, let's see what we got here. Okay, let's try this. I just want to do one part of it though. Let's just do this part. So I have this force, or this wire rather, that is at an angle of 45 degrees from the x-axis, and I want to know. I give you the current; it's 3 amps, and I want to know the magnetic force if the magnetic field is as shown. In order to do this, you first need to define what is L. So L will have both x and y components. The vector L will be Lx in the I direction plus Ly in the k direction. So you need to figure out what are those x and y components of L. I know this wire is 1.5 meters long, and I know this is an angle of 45 degrees. So I want to figure out what are the x and the y components of L. And then I can figure out what is the magnetic force on this wire. Sorry, I wrote K there. It should be J. What is this x? I don't know. Yeah, what is it? Not the sine of 45, although it turns out it's the same thing. Right, because 45 cosine is sine. What is it, Courtney? Right, so I'm going to find the magnitude of the vector, which is 1.5, times the cosine. Is this x component positive or negative? It's positive. What about the y component? It's negative. So we'll take the magnitude times sine of 45, and it's going to be a negative because this wire has a negative y component and a positive x component. Right, so you first want to find that vector. Does anybody have the x? What is the x? 1.5 sine cosine 45? Okay, I'm just going to call it, I'm going to call it 1.06 for now. I minus, it's going to be the same for the j. And now we want to know, actually to make this easier, let's just call this 1i minus 1j. Alright, and now I want to know what is the net magnetic force. So this is just a cross product. That should be pretty easy for you by now. Anybody have the force yet? It's gonna look like this. Alright, what is I cross K? Is it positive J? I never know. I always have to draw my coordinates. I have I, J. Some of you might be able to do this in your head. I cannot. I cross K. I is negative J. So this is 6, negative 6J. And J cross K, what is that? J cross K is positive I. Again, if you ever forget to draw your coordinate system, J, K is positive I. Alright, so J cross K is positive I, so that's minus 6I. I cross K is negative J. J cross K is positive I. Alright, once you get the cross products down, these are all pretty simple, right? They're pretty simple. We started dealing with 3D vectors. We're not really used to that, and dealing with the cross products is kind of new. I have a couple minutes left. Let's just do a few more of these quicker questions, and then we'll wrap up with this. I come away from this, yo? We're going to look at generators and electric motors next time. Alright, horizontal wire carries a current. What is the direction of the force on the wire? First of all, I can narrow it down to just a couple answers because I is in the X direction and B is in the Y direction. So Z has to be in the F has to be in the Z direction. Alright, I'll stop at 45, 45. Okay, good. E is the right answer. Fingers in the direction of I, B is up, so our thumb points out of the page. Horizontal wire carries a current in a vertical magnetic field. What is the direction of the force on this wire? Alright, I'll stop at 25. Huh? Right now? I'm sorry. Got it in? Okay. Alright, I'll stop at 30 then. Oh man. Alright, here, they're in the same direction, so if they're parallel or anti-parallel, there's no force at all. That's that sine theta term. Oh, we're gonna come back to this. We're not gonna do loops right now. We'll just wrap up there, y'all. Y'all have a good day, okay?